Hello students, Stride here again. Today we're looking at notes for 17.4, hearing and sound. So the illustration here, got very loud sounds for ear protection so you don't damage your hearing. So properties explaining behavior of sound. So we want to understand about speed, intensity and loudness, and frequency and pitch. Sound waves, longitudinal waves, and we have compressions and rarefactions on longitudinal waves, and I have to have a medium to travel through. And air, dry air at 20 degrees Celsius, speed of sound is about 242 meters per second. It will always take time for sound to travel from one place to another. Typically, sound travels fastest in solids, a little slower in liquids, and even slower in gases. This has to do with because the particles in a solid are closer together than they're in a gas or a liquid. Speed of sound depends on many factors, density of medium, and how elastic the medium is. Here's a number of speeds, say through gases such as air, slower, liquid water, salt water, a little faster. Salt water is a little more dense, a little faster in salt water than fresh water. Get to some solids, lead, cast iron, aluminum, glass, much faster. Do get some exceptions here. The lead, even though it's a solid, is slower than waters. So intensity and loudness. Intensity, the rate which as energy flows through a given area. Sound intensity depends on amplitude and distance from the sound source. Decibel is what we use to measure it with. For every 10 decibel increase, the sound intensity increases tenfold. A 0 decibel sound, barely heard, 20 decibels, 100 times more energy than a 0 decibel. 30 decibel, 1,000 times more than a 0 decibel sound. If we get over 90 decibels, that's when we can get hearing damage. So, prolonged exposures to things like just inside a bus, operating heavy machinery, a rock concert really high, taking off from the airplane taking off extremely high. At 120, actually can get pain caused. Loudness, the physical response to intensity. So loudness depends on intensity, but many other things like how well your ears work and how your brain interprets sounds, a lot of other physical responses to it. Frequency and pitch go together. Frequency is how fast it's vibrating. So in brass instruments, we get standing waves set up, longer tubing, longer wavelengths, lower frequency. So French horn can produce lower notes than a trumpet because you can get longer waves set up in it. Pitch is our perception of frequency. High frequency sounds have a high pitch, low frequency sounds a low pitch. Again, age, health of your ears affect pitch. Usually the older you get, the less you hear high pitch sounds. Ultrasound, the type of sound. Ultrasound frequencies beyond what we can hear. You have sonar, ultrasound imaging, some of our applications. So we tend to hear between 20 hertz and 20,000 hertz. Ultrasound is higher than we can hear. Infrasound, lower. Some animals will communicate in these frequencies. Sonar, we use it to determine distance underwater. Ultrasound imaging, nice medical technique. Here's an ultrasound picture. We got a thing we call the Doppler effect. It has a source of a sound approaches. We hear a higher frequency. When it moves away, we're going to hear a lower frequency. Doppler effect can be due to the motion of the sound, such as a emergency vehicle moving, motion of the listener, or perhaps both. So here's a person standing. Person A is going to hear a lower pitch. Person B is going to hear a higher pitch. And what happens as the emergency vehicle is moving closer, it causes the wave fronts to crunch together, making a higher frequency, higher pitch. On the back side, they're spreading apart, making them lower frequency, lower pitch. And a little bit about the ear. We got the outer ear, the inner ear, and the middle ear. Outer ear, as it's on the outside, it gathers and focuses sounds. Inner ear receives and amplifies. Inner ear then uses nerve endings and sends it to the brain. Diagram of thing. See the outer ear, we got the ear and the ear canal. Middle ear, we got three bones called the hammer, the anvil, and the stirrup. The eardrum separates the middle ear and the inner ear, or middle ear and the outer ear. The inner ear then consists of a thing we call the cochlea and the auditory nerves. So, part of the ear we can see called the outer ear. You got the ear canal. Eardrum, as I mentioned earlier, divides the outer and the middle ear. And the eardrum vibrates at the same frequency of the sounds striking it. Middle ear, the three tiny bones, the hammer, the anvil, and the stirrup. Three bones like a lever system, and it amplifies the motion of the eardrum. So it's an amplifier. And as it passes through them, vibrations from the stirrup travel into the cochlea. And we got a lot of hair-like projections there, and they vibrate. And we end up sending electrical impulses to the brain. Sound recorded actually works very much like the ear does. Converts sound waves into electronic signals. Can be processed and stored. And then we can convert those electronic signals back into sound waves to hear. Microphone, thing that's going to convert sound into electronic signal. And the microphone has many essential parts that the ear does. You have a vibrating membrane, like our eardrum. You have wires that would be like our nerve endings. But microphone changes the sound waves into electronic signals. And then we can, in a speaker, very similar to the microphone, only it's going through backwards, causing the membrane to vibrate, and then that sends sound waves through the air. So speaker changes electronic signals back into sound waves. Musical instruments can vary by pitch by changing our frequency of the standing waves. We can get a wide variety of sounds. Here it talks about wind instruments, stringed instruments, and some other stringed instruments, just different kind of instruments and how the waves are set up. Resonance response of a standing wave to another wave of the same frequency. Musical instruments use resonance to amplify sound, like on a guitar. The body of the guitar generates resonance to amplify the strings of the vibrating strings, the sounds produced. And here in music hall, all kinds of panels set up here, panels on the side. All these are to take care of making sure things aren't being reflected in the wrong way, to just give the best possible sound everywhere in the concert hall. Yeah, make sure you look over these questions and understand their answers. So that's all I'm going to talk about for section 17.4. That's all for now.